Hi, how is everybody?
I'm good. How are you?
Wow, I had just had a very unnerving class. So I'm using this service for class. I'm writing the notes on it. We started a little bit last class. You guys said that it was all okay. And we're like 2/3 of the way through class. I write it on a Word document because I think that's something that's accessible to everybody. And all of a sudden, the surface in front of me goes black. I'm not online anymore. The document disappears. So I open my Chromebook, and thankfully, by the time I got back into Zoom on my Chromebook next to me, everybody was still there. And when I got, the Surface to finally restart, but it wouldn't restart for a couple of minutes. Most of the Word document was auto-saved. But, oh my God, it's like my worst nightmare. It's like, the classroom it and everything's gone. So the only reason I'm telling you guys this story is because hopefully it doesn't happen again. That between the ending of that class and the start of this class, I don't have much time. After this class, I'm going to call OIT and ask them, help, what did I do wrong? But if everything goes black on my end, if all of a sudden I disappear, be patient and I'll try to pull something up. And I guess just in general, in case the Surface doesn't work, I'm going to have a plan B for giving notes. I don't know what it'll be, but yeah, see what happens. I think at the beginning of the pandemic, some of my coworkers put their phone as a camera to record like a Zoom meeting or whatever, and used a dry erase marker on their tubs around or something like that. Hopefully I won't be doing that. But oh my gosh, what a panic. So hopefully it won't ever happen again. Just like somebody told me that I should rain now. Somebody told me maybe the power went or something in a storm. I don't know, but oh my God. So if I'm a little frazzled, it's because I'm a little frazzled. Sorry about that, folks. How are you all doing?
All right.
Good.
I got two little kids here, so if you see anyone walking by, those are them.
How old?
6 and 4,
Oh,
boy and a girl.
Oh, what fun ages. At one point in time, my guys were like 2, 4, and 6.
Yeah.
And now I don't know what the hell happened. They're 30, 32, and 34. It was just yesterday. They were so enjoyable. They can. Well, you can, because it's yeah. All right. Now I'm sounding old.
Tough.
Before we get started, before I start taking attendance, I looked in my math lab, and from this class, I think I saw that 13 people were already registered in my math lab. Some of you had started doing homework already. Yay. Those of you who aren't in there yet, was it because you had a problem getting in there, or was it just because you didn't get in there yet?
I think I'm in there.
Okay. Is there anybody who had a problem with my labs? I know a few people sent me an email asking me what was the course ID, and my response is, if they ask you for a course ID, get out of there quick. Make sure you enter it through Blackboard, because if you put in a course ID, you no longer linked to Blackboard, and it makes a mess. And does anybody have questions on anything else, from last class?
I don't think so.
Okay, all right, then when I call your name, put your speaker on, please, and say hello to me. And we'll take attendance, and then we'll get started picking up from where we left off. Hopefully all goes well. Nicholas Albano.
Here.
Hi, Nick, how are you?
Good, how are you?
Good, good. Thomas Barber, how are you? Are you there?
Yeah.
How are you?
Good.
I liked your picture. Gianna Briglio.
I'm here.
Hi, how are you?
I'm good. How are you?
Good. Kayla Doherty, how are you?
Good, how are you?
Good. Brian Fitz? No Brian Fitz? Oh, I should open the chat in case somebody. Mary Franklin?
Here.
Hi, how are you?
I'm doing good.
Good. Charles Gray,
Here.
how are you?
I'm good. You?
Good. Jonathan, hi.
I'm here.
Hi, how are you?
Hi, thanks.
Good. Mohammed, Mo,
Here.
how are you?
Good. How are you?
Good. Valerie Ann,
Yeah, I'm here. You can just say Val. It's
Okay.
so much easier.
thank you, Val. I appreciate that. Brad, Al,
I'm here.
how are you? Steve Lee. Steve Lee. Elise Leeds,
I'm here.
how are you?
I'm good. How are you?
Good. Lauren Marble. Lauren. Jerome Marshall.
I'm here.
Good, how are you?
Good.
Good.
Uh-oh.
Miguel, how are you? I see your name there.
I'm good. How are you?
Good. Hannah Nixon, Hannah,
I'm here.
how are you?
I'm good. How are you?
Good. Olivia,
I'm here.
how are you?
Good, how are you?
Good. Alyssa N, how are you?
Here.
Olivia N. Oh, I'm going to mispronounce it again. Aventa?
Aviente.
I'm sorry, Aviente. I will get it by the end of the semester, I promise.
That's fine.
Don Tasia? I see your name there. I mispronounced it horribly, but I see your, at least on the screen. Christopher Salerno? No? Zach Schultz?
Hi. Hey, no, I'm here. Hello?
Oh, Chris, there you are. I'm sorry. I didn't see. I was looking for Christopher, not Chris. I'm sorry. And I didn't hear you. Zach, how are you?
Hello, how are you?
Good. Ryan Seps? Ryan S? No? Mike Slade?
I'm here.
How are you?
I'm doing good.
Good. Olivia Smith?
I'm here.
How are you?
Good, how are you?
Good. Morgan Spencer?
I'm here.
How are you?
Good, how are you?
Good. And Dominique Williams?
I'm here.
How are you?
Good, how are you?
Good. Is there anybody I missed?
I'm here.
Stephen, let me see. I got you now. Thank you. All right, then what I'm going to start doing is sharing my screen. And I'm going to start with this blank document and try to pick up from where we left off before we begin some information at the start. Today is September 2nd, 2020. We're going to look at expressions. And we're going to also look at sets. And in my lab's math, the introductory homework and homework P1, which is on a lot of what we're looking at today, are all due September 9th. When last we met, we looked at exponents, and we were talking about how, especially if we're working with sign numbers, how important it is to use parentheses. We're going to, we defined an algebraic expression as something that involves constants, your numbers, variables, and your symbols of operation. Today we're going to start at looking at the idea of evaluating an algebraic expression. And in order to evaluate an algebraic expression, a million years ago when I used to teach a general math class, you know, long before everybody was required to take Regents math in high school, I used to put this big long expression on the chalkboard with all sorts of different operations involved. And I just told everybody to do it. And in a class of 15 people, I would probably get about 10 different answers. And it was because everybody approached it in a different order. And I used to do that with them to stress the idea that if we all want to get the same answer, it's important that we use the same order. And so before we start talking about evaluating expressions, we really need to talk about that order of operations. And when I say order of operations, can I go on the assumption that that's an expression that everybody's heard before?
Yes.
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 All right, when I say order of operations, is there anybody where a silly sentence comes to mind? Something like, please, excuse, my dear, Aunt Sally. Anybody hear that one?
PEMDAS.
PEMDAS?
Yeah.
PEMDAS being the first letter of each of those words. Not gonna lie, I'm gonna admit to my own inadequacies to you guys. The reason I'm more likely to use please excuse my dear Aunt Sally than PEMDAS is because I'm one of those people who are spelling challenged. And if I can't spell real words, you know, I can't spell made up words. But they do the same thing. Did anybody ever hear the real silly one, purple elephants marching down a street?
No.
No?
Yeah.
Yeah, that one's a little bit more colorful than some of the others. But they all tell us the same thing. They all start with P. And can anybody tell me what that P represents?
Parentheses.
Parentheses. The parentheses. And what that tells us is when we approach a problem, we have to do the inside of parentheses first. When we talk about doing the inside of parentheses first, we have to realize that if we have nested parentheses, if we have parentheses inside of parentheses, you do the innermost first. And when we talk about parentheses, they don't always look like parentheses. There are other symbols of grouping, symbols that might include grouping. And so if I have something like a square root symbol, that's like a symbol of grouping and you do what's inside first. Or if I have something like absolute value bars, that's a symbol of grouping and you do what's inside first. And another one that might not be quite as obvious, if I have something like a fraction, oh, let's try that again. If I have something like a fraction, with a fraction, there are invisible parentheses around the numerator and around the denominator. So that if you've got a long algebraic expression that involves a fraction, simplify the numerator of the fraction first, there's parentheses around that. Simplify the denominator of the fraction second, there's parentheses around that. Or if you're one of those people who use a calculator to do all of the simplification, you've got to type those parentheses around the numerator and the denominator in order to get the correct answer if you're working a fraction with a calculator. After the P for parentheses, next is the E. What does the E stand for?
Exponents.
Exponents.
And for that matter, if I've got a lot of work to do inside parentheses, hopefully everybody realizes inside the parentheses, you would start with the exponents. After the exponents, the next two, the M and the D, it was brought to my attention over the summer that some people don't think of them as all one step. The M and D are the multiplication and division, and they're all in the same step, all at once. You do multiplication as they come from left to right. That's the problem with PEMDAS, and my dear, that's all together in a single step. Multiplication and division are treated equally. And in the same way, the A and the S, the Aunt Sally, that's all one step. It's addition and subtraction in the same step as they come from left to right. So, I glean that you're all kind of familiar with those. Let's look at some examples of how you might be asked to simplify or evaluate an expression. Can I scooch up or am I going too fast?
Okay.
So let's simplify each. And let's do the first one together. The first one, let's say I have 2 parentheses, negative 2, close parentheses, minus 4 parentheses, negative 2, close parentheses, over 5 minus 8. The order of operations says to do what's in the parentheses first. Does everybody notice in this problem, inside each parentheses, there's only a single value. So we don't have to really do anything there. But I want to remind you, because this is a fraction, there are those invisible symbols of grouping. We should look at this as parentheses 2, negative 2, minus 4, negative 2, close parentheses for the numerator, over parentheses 5 minus 8. You don't necessarily always have to write those parentheses in if you're doing your work by hand. But if you were trying to evaluate something like this with a calculator, those parentheses around the numerator and the denominator are important. So let's go through and let's work out the top and then let's work out the bottom. Inside the parentheses around the numerator and the top, inside those parentheses, is everybody familiar with the idea that when then these are written next to each other without a symbol, it means multiplication? And so what we've got here is some multiplication and some subtraction. What should I do first? Multiply or subtract?
Multiply.
Multiply. Great. And I'm going to take that multiplication as it comes from left to right. So 2 times negative 2 would be negative 4 minus multiplication here. 4 times negative 2 is negative 8. And then simplifying what's inside that parentheses. Does everybody remember the rules for subtraction? Minus a negative is like adding a positive. And so that's going to give me 4 in the numerator. In the denominator, inside those parentheses, I just have 5 minus 8. 5 minus 8 is negative 3. And so here my final answer would be 4 over negative 3. You're going to find a lot of times in my math lab, in the fine print behind where you put your answer in, they tell you to express as the ratio of integers in simplest form. So what the hell does that mean? That means I am done. This fraction does not simplify. I just want, if it's a ratio of integers, I just want a single fraction. Do not change it into a decimal. Do not change that improper fraction into a mixed number. You're going to stop there. In stopping there, how you type it in, you've got a few options. Is everybody familiar with the idea that if I have the fraction 4 over negative 3, that means like positive 4 divided by negative 3, and a positive divided by a negative would give me a negative number. So I could write that as the fraction 4 over negative 3. I could also write that as the fraction negative sign out in front of the whole thing, negative 4/3. And I guess if you really, really wanted to, you could also write that as negative 4 over 3. Is everybody familiar with the idea that those three fractions all have the same value? And as long as there's just one negative sign, it doesn't matter if you put it in the numerator, the denominator, or out in front of the whole gosh darn thing. We good?
Yep.
Yep. Okay, then I'm going to put 2 more up, and I'm going to shut up for a minute and ask you folks to try to simplify these 2. Give you a few minutes, and then we'll go over them together. First one, I'm going to have 8 minus 3 parentheses, negative 2 parentheses, 5 minus 7, close parentheses, minus 5 parentheses, 4 minus 2 squared, close parentheses, close parentheses. And the second one, I'm going to leave a little bit of space, is 9 plus 3 parentheses, x minus 2, close parentheses, to the third. And with this one, we're going to say when x equals 4. This is one place where I hate doing this through Zoom and not in the classroom. Where in the classroom, I'd be walking around and looking over people's shoulders and seeing how they're doing. I can't do that. How are you guys doing with this? Should I wait a minute longer?
Yes, please.
Okay. Are we ready to go over the first one?
Yes.
Yeah.
Anybody brave want to volunteer to me what you got for the first one?
-4.
Yep, I got -4 too. Just in case anybody did it, let's go through it slowly.
Yeah, I have a question.
Sure.
So, like, it's in the first line when it goes -5 times 4 minus 2 to the second.
Uh-huh.
So I think that's where I messed up. I'm just gonna call myself out because I thought it would be -2 to the second, which would make it a positive 4.
All right, I thank you very much for volunteering that. I like that you're starting inside the parentheses.
Yeah.
But now when I'm inside these parentheses, what should I do first? Does subtraction come first or do exponents come first?
Oh, the exponents. Okay, so like that's where I got confused because it's a subtraction. I thought it would make that -2.
No, you have to do those exponents first.
Okay.
So inside of there, and thank you, that's the perfect place to start. That's where you should start. So inside those parentheses, that ends up being 4 minus 4 or 0. So that part of the problem becomes -5 times 0.
Okay, thank you.
This part inside these parentheses, 5 minus 7 would be -2. And so now what we've got inside the big parentheses is -2 times -2 minus 5 times 0. And again, we've got subtraction in here, but remember we've got to multiply before we subtract. So that becomes -2 times -2 is 4. And then over here, 5 times 0 is 0. And so inside the parentheses, what we've got is 4. And I got a little lazy, sorry folks. I was just focusing on that first step parentheses, inside the parentheses. I didn't mean to lose the rest of the problem. It's 8 minus 3 times that, 8 minus 3 times that, 8 minus 3 times that. Now when I look at what's left, what should I do first? Subtract or multiply?
Multiply.
Multiply. So that becomes 8 minus 12, and that's where that -4 comes from. Order of operations when we're working inside parentheses. Inside that parentheses, we still have to stick to our order. Now the next one, I played a trick on you guys. I introduced a variable. I introduced that x. The way this is written, help. What should I do with that x? Substitute.
Put it in.
So is everybody all right? We're going to substitute
Yes.
for the variable if we're given a value. And so this is really 9 plus 3, parentheses, 4 minus 2, close parentheses, to the third. Now that there's no variable left, is everybody okay? First place we start is P, parentheses. In the parentheses, 4 minus 2 is 2. That's 9 plus 3 times 2 to the third. After parentheses, the next thing is exponents. 2 to the third is 8. So that's 9 plus 3 times 8. After exponents, we do multiplication and division as they come from left to right. So that gives me 9 plus 3 times 8 is 24. And then my last steps, addition and subtraction, as they come from left to right. That one, did everybody get 33?
Yes.
Great. Great, 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 great. If that's all right, and I know the ones in the homework get a little bit uglier than this, and don't let them be stressful. If you need help, please use that email my instructor. please use that help me solve it, or please ask at the beginning of class if there's a question in the homework that you're getting frustrated with. And I don't make the homework harder than the examples in class to be mean. I do it because it's supposed to help you learn. There's something called a productive struggle, where if you have to work a little bit harder on something and it's not all spoon-fed to you, you remember it better. And so the homework gets a little bit more challenging than some of the in-class examples. Intentionally, it's supposed to make you learn better. Does anybody else notice that if somebody just shows you what to do,
Can you go back up?
but you don't remember, you need me to go back for a minute?
Yes, please.
Okay. As opposed to, if you have to really work hard to figure something out, you're more likely to retain it. So, all right. So, after looking at these order of operations and simplifying these expressions, the next thing that we look at are sets. And we're not going to do a lot with sets, but there's a little bit of set notation that you need to be familiar with for this class. So let's go through and let's do some definitions and some notation. My 9 o'clock class this morning, my contemporary math, we spend a quarter of the semester looking at some of the intricacies of set theory. Here, we just need to be able to recognize and use the notation. When I talk about a set, does anybody know what I mean?
Is that like the number line thing?
Yeah, it's going to eventually lead to the number line thing. And in this class, we're going to mostly talk about number sets. But in general, a set is just a well-defined collection of objects. And again, I'm guessing that in an algebra class, you folks might have once heard of something like a solution set, and that would be a number set, the set of numbers that makes an equation true. But when we're talking about sets in general, they could be sets of anything. I could talk about the set of students in the class if I wanted to. When we look at a set, we show them in a couple of ways. One way is by description, and another way that you frequently see a set is to list it by roster. When I list by roster, I use braces. And braces are those like funny looking parentheses. They almost look like a profile or something with a nose in the middle. Sometimes in the homework, you're going to see things that ask, what's the solution set? And a lot of times those braces are there for you, and you just need to fill in the elements. So when we list by roster, we use braces. We put the elements inside the braces. It's important. Oh, what happened? It's important that you put commas between the elements. And going back to a theory that I strongly hold to, which is that mathematicians are intrinsically lazy and don't like to write, you do not repeat the elements. If something's in there once is sufficient. There's no reason to put something in there a second time. You guys, I'm getting scared. The computer's beginning to do weird things on me. That's what it did last class. It started jumping.
Crazy.
What?
That's crazy how it glitches.
Yeah,
Is
that's
it
what I
an
get.
old one? Like an older computer?
I don't don't think so. I think it's a relatively new surface that I got. It's the college's, it's not mine. After class, I'm gonna call OIT and ask what I'm doing wrong. Let's see. Maybe if I close this up, maybe if I close this up, I have less things open. What the heck is that? Are you guys still there?
Yep.
Yes.
Okay.
Yeah.
Okay, Word's not responding. I'm just gonna wait for a minute. I'm looking for a whiteboard because I know there used to be a whiteboard option. Okay. Well, I'm going to just draw on the screen that's in front of me. And if you guys are all right, I'm giving you the same notes and the same examples that I gave the other section. Would it be all right if I just posted the written document from the preceding class? Okay? See what happens. And so you do not repeat elements. And when I talk about the elements, I mean the things inside the set. Now, couple of things. It's not going to move. I'm going to just leave it there. Let's look at an example. Let's say S is the set 1, 2, 3. And does everybody see that that's a set that has 3 numbers in it?
Yep.
Yes.
Yes.
Set, if I say T is the set 1, 2, 3 without the commas, does everybody see that that set just has 1 number in it, 123?
Yes.
And I know it's a silly example, but is that enough of an example to highlight the importance of commas?
Yes.
Also, notation-wise, has anybody ever seen this funny-looking symbol? Kind of looks like a weird E.
No.
Say it again.
No, I've never seen that one before.
Okay, does it look like an E to you?
It does.
The fact that it looks like an E helps me remember that it means element. Oh. And so, if I look at that first set, does everybody see that I can say that 2 is inside of S? So I'll say 2 is an element of S. When we use this notation, the element has to be on the left of the symbol and the set has to be on the right. Now, I'm going to go again and I'm going to look at that set S and I'm going to say, is 4 an element of S? Is 4 inside of that set S that we had defined?
No.
No. Does it make sense then? I'll put a slash through it. and with a slash through it, that's going to mean not an element of. And when we look at sets, we can see sets of all different sizes. And one set that we see a lot is the empty or null set. When I refer to an empty set, does it make sense that if a set's empty, there's nothing in it? The
Yeah.
way in which I could show that is I could have my braces with nothing in between them. Is that set empty or what?
Yes.
Another symbol for the empty set is actually the symbol for the null set, and that's a 0 with a slash through it. So those two symbols, the braces with nothing on the inside and the 0 with a slash through it, both mean the same thing. They both mean that empty set, a set with nothing in it. But you have to be careful. Sometimes people go overboard. Sometimes you see people do the braces and put the 0 inside it. As you look at that one, do you see how this set, there's something in the braces, so this set is not empty. All right? So empty set, if there are braces drawn, you're just going to leave it blank, not put anything in there. If there are not braces drawn and they want the empty set, on the toolbar in my math lab, there should be this symbol, the 0 with a slash through it. All right? Everybody got this down, because since I don't know how to save the blank screen, so I'm going to clear it and start over again. It's like erasing the chalkboard. Are you guys okay?
Yeah.
Yes.
Yep.
When is an empty set or a null set ever useful?
Have you ever, in your mathematical career, have you ever been asked to solve an equation, and when you go through and you do all the work and there's no solution? If you were asked for the solution set and it was empty, it would be a null set. Another time that you might see something like an empty set or a null set might be when we look at where we're going next, some set operations. And the way we do things like addition and subtraction with numbers, there are a couple of things that we do with sets, a couple of different operations that we can use. The first one, and I'm getting back, don't think I'm skirting your question. I'm going to get back to a place where we'll get an empty set, I promise. First set operation that we talk about is intersection. And when I talk about the intersection of two sets, the symbol for intersection looks kind of like an upside down U. I've heard it called the cap. I think hearing it as a cap, it almost looks like a knit cap or something like that. But that's an intersection, the symbol for intersection. Now, to help me remember what the intersection of sets mean, I think about how we use the word intersection in normal conversation. When I talk about an intersection, is there anybody else in the room who pictures two streets crossing? And if I'm standing over here, I'm in the middle of the horizontal street. If I'm standing over here, I'm in the middle of the vertical street. But if I'm standing over here, aren't I standing somewhere in the intersection? And isn't the intersection of two streets the piece of blacktop that they have in common, where they overlap? Everybody with me?
Mm-hmm.
And so when I look for the intersection of two sets, the intersection of two sets is the set of elements common to both, where they overlap, what they have in common. So if I look at an example, my first set, I'm going to put in 1, 2, 3, 4. My second set, I'm going to put in 2, 4, 6, 8. And I want to take their intersection, so I'll use that symbol for intersection. And so what I'm asking is, what do they have in common? Where do they overlap? Do they have anything in common? Is there anything in the first set?
2 and 4.
2 and 4.
2 and 4. And so the intersection of those two would be the set 2 and 4. Okie dokie?
Yes.
Instead, if I have the set 1, 3, 5, and I take its intersection with the set 2, 4, 6, what do they have in common? Is there anything that shows up in both sets?
No.
No. And so here, this would be an example where we'd need that empty set or that null set to describe what's going on. Their intersection is empty. They have nothing in common. Is that an okay example of where you might have an empty set?
Yes, thank you.
Okay. Where that might also come into play is when we go and solve systems of equations. There are some systems that have no solutions. It's kind of like if you would be looking at parallel lines that never cross. Their intersection is the empty set. They have nothing in common. Okay? Intersection good. Can I clear the screen?
Yeah.
Yes.
Yes.
And again, I promise I've got these words written down from, oh, it's back. Let's see. Let me get rid of draw. Let me exit that. And nope, it was just kidding. Let's see. Annotate. We'll go back there. Next set operation that we're going to look at is the union of two sets. And when I think of the word, the union of two sets, it makes me think of something like a labor union. And at least back in the day, everybody was in the union. Union included everybody. And so the union of two sets and its symbol is the great big U. U is for union. It's all of the elements of each set. So we're just combining the sets. We're taking everything from each of them. So I'm going to go back to the two sets that we started with. If I have the set 1, 2, 3, 4, and I want to take its union with the set 2, 4, 6, 8. When I take the union of the sets, I want to include every single element of each set. And so from the first set, I have to have 1, 2, 3, 4. From the second set, I need a 2, but you guys see there's a 2 in there already?
Mm-hmm.
Don't repeat. Don't write it a second time. It's in there already. I need a 4. That's in there already. What I have to add is the 6 and the 8. And so when I look for the intersection of two sets, I say, where do they overlap? What do they have in common? When I look for the union of two sets, I look for all of the elements of both. I kind of just throw them all together. It's like you're making a stew or something and you just throw everything in the pot. All right?
When you find like the intersection and the union, do you have to put them in like chronological order?
No, order should not matter.
Okay, so I can do like 3, 2, 6, 8 as long as it's all in there.
Right. As long as they're all in there, order does not matter.
Okay, cool. Thank you.
Okay. Unless the directions say put them in order.
Okay.
There's one place in one of the homework assignments when we are looking at rational functions and doing operations on algebraic fractions. When they ask what you exclude from the domain, I think they tell you that you have to put them in order. And the number of times I've had students banging their head against the wall because they've got them all, but they're not in order, so my math lab doesn't accept it. So read the fine print. If it says in order, put them in order, okay?
Thank you.
And I agree with them. I bang my head against the wall asking what they did wrong. Another thing with sets that we talk about are subsets. The subset of a set is a set, each of whose elements is in the original set. There's a symbol for that. And in Mr. Blitzer's algebra book, the only symbol that he uses for a subset is this. And as I look at that symbol, does anybody look at that one and see kind of like a weird looking C? And the fact that it looks like a C reminds me that it's like saying it's contained in. And so, for example, let's say I have a set that has a 1 and a 2 in it, and my second set has 1, 2, 3, 4. Is every element of the first set inside the second set?
Yes.
So we'll say that the first set is a subset of the second set. It's like saying the first set is contained in the second set. Another example, what if I were to reverse it? What if I were to have 1, 2, 3, 4, and 1, 2? Is every element of the first set inside the second set?
No.
No.
So we would say that it's not a subset. All right. So if one set is a subset of the other, it's all contained within it. And I think there's a couple of questions in my math lab that ask about the intersection and union of sets. But there's also a few questions that ask you to identify elements of special number sets. So the next place we're going to go is to look at some special number sets. Is everybody all right if I clear the screen?
I have a question.
Sure.
Is a null set contained in every set?
Yes. What happens is I'm going to look at the empty set. And I'm going to look at the set 1, 2. I'll just look at the set 1, 2. Oh, Lord. Now, up here, 1, 2 was a subset of 1, 2, 3, 4 because they're in there. Why was 1, 2, 3, 4 not a subset of 1, 2? Because it had this extra stuff. So if it's not a subset, it means it's got stuff in there that's not in the first set. If I look at the null set, the empty set, there's nothing in there. So it has no extra set. And so it's considered a subset of every set. Good question. The empty set, the null set is considered a subset of every set. All right?
Thank you.
You're welcome. Can I clear?
Yes.
Then let's look at some number sets. And the first number set that we're going to look at is abbreviated with an uppercase N. And that N stands for the natural numbers.
I have a question.
Sure.
Just to like get my notes in order. Are number sets part of set operations?
No,
Okay, so
we'll do
okay.
the operations on different sets of numbers.
Okay, thank you.
And if I was writing this all on one single sheet of paper, if Word agreed with me, I would have put a line in between them. So,
Okay, thank you.
the first set of numbers that we look at are the natural numbers. Sometimes people call them the counting numbers. And that idea of counting numbers. Can you guys, any of you remember being a really little kid? And when you first started learning about numbers, you'd start counting. And when you count things, don't you start with 1? 1, 2, 3. And if you really enjoy counting, I'm going to put the ... here. Because if I really wanted to, I could spend the rest of my life counting. It's an infinite set. But the natural numbers, the counting numbers, just like when you count, you start counting with 1. Yes?
Yes.
Next set of numbers, a lot of people, it doesn't look a lot different. But if you ever get into set theory and numbers theory, there's a significant difference between the two sets. The next set of numbers is abbreviated with a W, and that W stands for the whole numbers. And the difference between the natural numbers and the whole numbers, I remember when I first learned about them, I was told the differences between them is that the whole numbers start with a whole. If I asked you to draw a whole H-O-L-E at the beginning on your paper, wouldn't you draw a circle? And so the whole at the beginning of the list is the number 0. So the whole numbers start with 0. 0, 1, 2, 3.
Do those include negatives?
No. Whole numbers just include 0. And again, 0 is a special number. It's the additive identity. We can add 0 to any other number. And it doesn't change its value. It's got the 0 multiplication property. When you multiply by 0, you get 0. And so 0 is a very important number in the number set. And so adding 0 makes that significant difference. What you're talking about, the next set of numbers, believe it or not, is abbreviated with a Z. And those are the integers. And the integers are where we add the negatives. And so the integers are infinite on both sides. We've got dot, dot, dot. Then we might have -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So the integers include all the whole numbers and their opposites.
Can we go back to whole numbers real quick?
Yeah?
So whole numbers always start with 0?
Yep.
So could it be like 0, 2, 4, 6, 8?
0, 2, 4, 6, 8 would be whole numbers. That would be a subset of the whole numbers.
Okay, so it's
But
just
the difference between the natural numbers and the whole numbers is 0.
okay. Thank you.
Okay, thanks for asking. Now, oh dear. Okay, let's see if it lets me scroll to a blank page. It doesn't. So let's see. No? Okay, I'm going to exit this Word document and try just starting a new one. And now it's not responding and letting me. That sort of looks interesting with writing on top of writing, huh? Okay. Now, let's see. You guys, I'm sorry about this. I don't want the recovered files. Oh, I want a blank sheet. Okay, is that better? Sorry about that. So as I look at those number sets, I'm going to clear it. Can I clear it?
Yes.
Go ahead.
Does everybody see that all of the natural numbers are contained in the whole numbers, and all of the natural numbers and the whole numbers are contained in the integers? And so the natural numbers are a subset of the whole numbers, which are a subset of the integers. All right? Next set of numbers that we talk about are a Q. And Q are the rational numbers. And when I look at that word rational numbers, inside that word rational, does everybody see the word ratio?
Yes.
And so rational numbers are numbers that can be expressed as the ratio of integers. And are you folks familiar with the idea that a ratio can be written with a colon, but it also can be written as a fraction? And to say that they're the ratio of integers means that they can be written as fractions. And I know every semester there are some students that tell me when they learned about rational numbers, they learned that they are the terminating decimals or repeating decimals. So, for example, hopefully everybody's familiar with the fact that 1/2 as a decimal is 0.5.
Mm-hmm.
And it's a terminating decimal, it ends. As opposed to, is everybody familiar with the idea that 1/3 is 0.333 repeating? And so if a number can be written as a repeating decimal or a decimal that ends, it's a rational number. Now, the other number sets we wrote in roster, we were able to put the ... to say they went on forever, but we could start listing them with a comma in between. What's interesting about the rational numbers is we can't do that. Because if you think about in between any two fractions, there's an infinite number of fractions. If I look between, let's say, 0 and 1/2, I could have a quarter, I could have an eighth, I could have a 16th, and in between them, I could spend the rest of my life just filling in that little space. And so we can't do the comma and the ... So instead, with the rational numbers, we need to use something different. I'm not sure you're all familiar with this. Can I clear the screen, guys?
Yep.
Yeah.
We need the set builder notation. And when we use a set builder notation, what we do is we have a brace for our set. Then we put a variable to represent what's in the set. Because there's so many things in that set, we can't even start trying to list them. So we'll use a variable to represent it. But to just throw a variable in there does no good. And so then we put a bar, and the bar is read as the words such that. And what follows the bar is a description of what the variable represents. And we put all of that in between our braces. So what the heck does that mean in terms of our set Q, our set of rational numbers? Well, we just talked about the fact that we can't list them because there's so many. So I'll say Q is the set of all X. I'm going to use the variable X to represent any of those rational numbers such that, and then how did we describe our rational numbers? We said they could be written as fractions. So X is going to be able to be a fraction. We'll say it's A over B. But that's not enough because we have to say what are A and B. Well, A and B have to be integers. So they're elements of the set of integers. And then there's a technicality. I'm picking your brains to see if you can remember. Everybody's worked with fractions before, yes?
Mm-hmm.
Yes.
Can every number go in every place, or is there something that we have to watch out with?
B can't equal 0?
B can't equal 0. We cannot put a 0 in the denominator of a fraction. And so the rational numbers, Q, are the set of all numbers such that they can be written as a ratio A over B, where A and B are integers, but the denominator cannot equal 0. How cool is that?
Complicated.
But the symbols, the reason math people do that is it's a heck of a lot less writing, and you don't have to spell, yes?
Yeah.
So, and the reason it's the way I can justify, I'm not sure if it's the reason that it's a Q or not. The way I can justify rational numbers being Q is because what's the one Q word you hear in math? Quotient. And quotient means division, and fractions mean division. So Q, the rational numbers, is a set of all x such that x can be written as a fraction, A over B, where A and B are integers, but the denominator can't be 0. Those are our rational numbers. And what happens is all of the integers, which are whole numbers, all the natural numbers, I apologize, which are whole numbers, which are integers, are also rational numbers. Because if we think of a number like 2, we can write that as 2 over 1. And so our rational numbers include all of those other sets. Next set of numbers is a little quirky because it's one thing that we are going to define by what it is not. Does everybody have all of this written down? Can I clear it?
Yes.
Yes.
Okay. And again, I can't post what we're doing because I don't know how to save it, but I'm giving you identical to the notes I gave the other class, the other section, so I'll post their notes for you. But the next set are the irrational numbers. And when we use the word irrational, if somebody's irrational, doesn't that mean they're not rational?
Mm-hmm.
Irrational numbers are numbers that are not rational. They cannot be expressed as a fraction. If they can't be expressed as a fraction, what they are our non-repeating decimals. Can anybody think of a non-repeating decimal? Is there any number that you're familiar with that would be a non-repeating decimal?
Pi.
Pi, beautiful. How about something like the square root of 2? Or the square root of 3? Or the square root of any number that's not a perfect square? So, now I'm going to get real silly on you. Your world, is it made up of rational people and irrational people? Yeah?
Yep.
And when you put them together, you get the real world?
Yep.
Instead of real numbers, which is this big goofy looking uppercase R letter, I can't draw it pretty enough, is the union of the rationals and the irrationals. And so it's putting all of the numbers that you know of to this point together. We're staying real. We're going to wait a couple weeks before we start using our imaginations. But when we talk about the real numbers, it's the rational and the irrational together. And if you folks are all right, that is exactly where I stopped with the other section. We got to the point of we're going to next start looking at number lines. All right?
Why is I not irrational?
Because I turns out to be imaginary. And so I don't know of a single abbreviation for the irrational.
Have a nice day.
But I are imaginary. Yeah, have a great day, you guys. And let's see, I think I have to stop sharing the screen. When I post the class, it'll be a Zoom recording, not a YouTube. And I'll call OIT about what I can do to save the written word. Otherwise, I might just be saving the recording of the class. Okay? We'll see what I can do. Sorry about that. It's just me and technology. I don't know. So I hope your day goes, the rest of your day goes better than mine has to this point. All right?
Have a great day.
Hi.
Bye-bye.
Bye-bye.